Welcome to Daily Papers, the podcast where we break down the latest research into bite-sized, easy-to-digest pieces.
Imagine going for a medical scan. You want it to be fast, safe, and give your doctor a crystal clear 3D picture of what's going on inside your body. What if that technology could see deep into your tissues with incredible detail, helping to spot tumors or check blood flow in the brain, all without any harmful radiation?
That sounds like the holy grail of medical imaging, and it's the exact future that a new paper from researchers at Caltech and NVIDIA is trying to build. They're taking a really clever imaging technique and making it faster, cheaper, and more powerful using a new kind of AI.
The technology at the heart of this is called photoacoustic computed tomography, which is a mouthful, so we'll just call it PACT.
Okay, so it's got photo for light and acoustic for sound. How on earth do you combine light and sound to see inside the body?
It's a brilliant trick of physics. First, you shine a very short pulse from a harmless, special type of laser onto the skin. This light travels into the tissue where it gets absorbed by certain molecules, especially hemoglobin, which is the protein in our red blood cells.
So it lights up our blood vessels?
Exactly. And when these molecules absorb the light energy, they heat up by a tiny fraction of a degree. This sudden, minuscule heating causes them to expand instantly, creating a very faint pressure wave, basically a sound wave.
Like a microscopic clap of thunder inside your tissue?
That's a perfect way to put it. And then an array of super sensitive microphones, called ultrasonic transducers, listens for these tiny thunderclaps. By measuring exactly when the sound from different locations arrives at each microphone, a computer can work backward to pinpoint where the sound came from.
And by mapping all those points, you build a detailed 3D image of the blood vessel network deep inside the body. That's incredible. So what's the catch?
The catch has always been the hardware and the time. To get a really sharp 3D image, you need a huge number of these ultrasonic sensors, often arranged in a big dome or a bowl. You also need to take a lot of measurements, which makes the process slow.
Right. The paper mentions that a 3D breast scan could require a 10-second breath hold. That's not ideal for patients, and it sounds like the equipment would be incredibly expensive and bulky, limiting its use in a typical clinic.
Precisely. This is the problem the researchers set out to solve. How can we get the same high-quality 3D images, but with far less equipment and in much less time?
And I'm guessing the answer involves artificial intelligence. The paper introduces a new model they call PANO.
That's it. PANO stands for Packed Imaging Neural Operator. It's an AI model custom-built to reconstruct these photoacoustic images, and it does things very differently than previous approaches.
How so? I know AI has been used in image processing for a while.
Well, many older methods work in two steps. First, a traditional algorithm would create a rough, often blurry and artifact-filled image from the raw sensor data. Then a second AI would act like a denoiser, trying to clean up that messy first draft.
It's like trying to fix a really blurry, grainy photo with a fancy software filter. You can improve it, but you can't recover detail that was never there in the first place.
You've got it. PANO, on the other hand, is what's called an end-to-end model. It skips the messy first draft entirely. It looks directly at the raw sound signals picked up by the sensors, and in one clean step, it generates the final high-quality 3D image.
So what's its secret? The paper uses this great term, physics-aware.
This is the cleverest part. PANO hasn't just been trained by looking at thousands of before and after pictures. It has also been taught the fundamental laws of physics. It has the Helmholtz equation, which describes how sound waves propagate, baked right into its learning process.
So the AI isn't just making a pretty picture that looks plausible. It's constrained by physics to generate an image that is actually consistent with the sound waves that were detected. It literally cannot create an image that would be physically impossible.
Exactly right. This prevents the AI from hallucinating details and makes it incredibly robust. And because it's a special type of AI called a neural operator, it learns the underlying physical relationship, not just a pattern. This means it's super flexible. You can train it on data from a full set of 1,000 sensors, and it still knows what to do when you only give it data from 100 sensors. It doesn't need to be completely retrained.
Which is key to making the system cheaper and faster by using fewer sensors. So the big question, how well did it actually work?
The results are pretty stunning. They tested Pano against the traditional methods and the two-step denoiser AIs using both computer simulations and real-world phantom objects.
And what did they find?
In scenario after scenario, Pano came out on top. Even when they drastically reduced the amount of data, what they call sparse sampling, Pano was able to reconstruct clear, sharp 3D images of complex branching structures.
I'm looking at some of the result images in the paper now. The difference is night and day. With sparse data, the old methods produce images that are a blurry mess, full of streaks. But the image from Pano is incredibly clean. You can see all the fine details.
And it's fast. Pano can reconstruct an entire 3D volume in about 1/10 of a second, which is easily fast enough for real-time interactive imaging.
So, bringing this all together, what's the big picture implication of this work?
It establishes a practical path for making 3D packed imaging dramatically more accessible. By using a physics-aware AI like Pano, hospitals could potentially use cheaper machines with less hardware and get faster, higher-quality scans.
Which could be a game changer for applications like cancer screening, studying brain function, or even guiding surgeons in real time. It's a huge step towards getting this powerful technology out of the research lab and into the clinic, where it can actually help people.
It's a perfect example of how combining the raw power of modern AI with the timeless principles of physics can create something truly revolutionary.
A fantastic glimpse into the future of seeing inside ourselves. That's all the time we have for today.
Thanks for tuning into Daily Papers.